Hey, welcome everybody. I'd love to introduce Konstantin Batygin from Caltech, who's been, doing a lot of fun data analysis, trying to find, a new planet in the solar system based on its impact on the rest of it. So welcome, Konstantin.
Thank you. It's a real pleasure to be talking with you all this morning. I do apologize for, not having the ability to go all the way up to 10 a.m. I do have to jump on a flight, but I'm excited to share this research with you all and talk about some of the modeling efforts that we've been doing really over the last decade to understand the dynamics of the outer solar system. Greg, can you still hear me like this?
Yeah, all good.
Okay, cool. So should I just get right into it?
Oh yeah, please, yeah.
Okay, cool. And yeah, just Greg has already mentioned this, but please feel free to send him questions, interrupt me along the way, all of these things, because I get overexcited about planets and I have a tendency to just talk indefinitely about the outer solar system. So please feel free to stop me along the way. Okay, so getting into it, I would say between, if we are to kind of think about the last 3 decades and detection of extrasolar planets, right, planets that revolve around other stars. And I would say the third has been the detection of the second kind of asteroid belt of the solar system. And a lot of people are familiar with the asteroid belt, which is full of asteroids that live between Jupiter and Jupiter and Mars, right in that wedge there. But as it turns out, the solar system beyond the orbit of Neptune has an additional field of icy debris, which is much more massive than the asteroid belt that we are used to, at least in order of magnitude. And it kind of occupies this interesting dynamical domain where orbits, as can be seen on this animation, kind of form a donut. So this donut of orbits is conventionally called the Kuiper Belt. I've been lobbying to call it the Dunkin' Donut because, in fact, it was predicted not so much by Kuiper but by Martin Duncan. But that aside, this detection and the kind of characterization of the orbital structure of this field of debris has, in the last really 20 years, completely reshaped our understanding of how the solar system evolved in the first few tens to 100 million years of its lifetime. And perhaps the most basic question you can ask is these icy, planetoids, how did they get there? Like, why does this field of debris exist beyond Neptune? And the answer turns out to be remarkably subtle, and it's rooted in the fact that the planet planets of the solar system formed on somewhat more compact orbits. Sorry, was there a question?
Yeah,
Yes,
we're kind of losing your voice, and I think it's because of the animations and your bandwidth. So maybe if you didn't have animations, it would help.
Okay. Let's see. Let me try one more thing, actually. Let me try going like this. Can you hear me better like this?
Yeah, I mean, it just keeps coming in and out, so I'll let you know.
Oh, okay. Yeah, sorry about that. Yeah, I suspected it might also be like the blaring music at the airport. Okay, so yeah, maybe I'll skip the animations and kind of skip between slides. So yeah, like one of the things that has been remarkable is we realized that the giant planets, Jupiter, Saturn, Uranus, Neptune, right, started out maybe a factor of 2 on smaller orbits, and were initially encircled by a ring of debris, ring of planetesimals that cumulatively weighed about 20 Earth masses. And as the planets scattered these debris outwards and kind of ground through this field of icy debris, the planets temporarily suffered an instability, right? Like a roll. like a bona fide orbital dynamic instability where the orbits of Uranus and Neptune in particular became much more eccentric, much more elliptical than they are today. And as this process kind of came, unfolded through dynamical friction, the planets settled back into the configuration that we observed. That encircled the giant planet 4.5 billion years ago. And this model, this instability-driven model of the evolution of the solar system, has been remarkably successful in explaining a whole bunch of stuff, right? Like you can read off all kinds of details about the dynamical structure of the Kuiper Belt from these types of n-body simulations. But one of the things that this model has not been able to explain, this instability scenario, is why the structure of the outer solar system appears to be confined if you look at long enough or large enough orbits. So can you all see this slide here, this video?
Yeah.
So we've got the orbits again of Jupiter, Saturn, Uranus, and Neptune. And if we now zoom out substantially beyond what we see, what we were looking at on the previous slides, right? The longest period orbits that we know of today, things that take 10 to 20,000 years to go around the sun, then without even doing any sophisticated computation, you can see that something is going on. First of all, the orbits, right, around appear to be tilted with respect to the plane of the solar system in a common way by about 20 degrees. Right? And secondly, they all point into the same direction. I mean, you guys have seen this too, right? These orbits are all pointing to the okay, this is kind of should be axisymmetric unless there is a torque applied. So over the last decade, this pattern has kind of been reinforced. So the previous animation you saw was from about a decade ago. And in 2017, the data looked like this. In 2019, more orbits detected. And by 2021, the data sort of more or less tripled. And what you see is that this pattern of clustering of the outer solar system is not only there, it correlates strongly with the long-term stability of this region. So let me dwell on that for just a second. Right? If you look at these distant bodies, these small kind of icy asteroids, whose orbits are shown here in purple, gray, and green, as they go around, some of them will hug the orbit of Neptune, and those objects are unstable. The gravitational three-body problem is famously chaotic, and the unstable objects will just get scattered away to infinity. And so the green orbits are things that you can think of as being on their way out of the solar system, and their dynamics are being messed up by Neptune's chaotic scattering. Conversely, the purple orbits are the ones that are dynamically stable. If you let them go, not much will happen to them other than that their orbits will slowly process, slowly over billion-year timescales, rotate around the angular momentum vector of the solar system. Okay, so seeing, if you kind of believe your eyes, yes, sir.
We're not seeing your slides anymore. We're actually seeing you now. But actually, it's a good time to maybe, as you said, just to understand some of the dynamical terms you're using. So first of all, when you say dynamic friction, are you thinking of collisions that stabilize orbits, or more like everybody tugging at each other and keeping each other like gravitationally tugging and keeping each other homogeneous?
Sorry, Greg, you disappeared there for a second. Can you repeat the question?
Yeah. when you say dynamical friction, which kind of stabilizes orbits, is this phenomenon of planets smashing into each other, or more gravitational tugging? And is it like they become more homogeneous in their orbits, or what's the dynamic there?
Yeah, so the dynamic there is actually similar to what would happen if you submerge the hot body in a cold bath, right? You can think of the planets, right, as big objects, right, that have a lot of gravity, and around them is a large population of small objects, which cumulatively have the same amount of mass, but individually are tiny. Okay, so if you think about the equal partition, like if you think about the state to which to which the system wants to go, it wants to go to a state where there's an equal amount of energy and angular momentum in the big and the small bodies. And this means that the small bodies get puffed up, they kind of suck out the free energy from the orbits of the big ones. So as a consequence, the planets settle to the plane and circularize at the expense of exciting the orbits of every small particle. So it's a little bit like a gravitational version of the second law of thermodynamics. Or if you were to take a hot bomb and put it into a cold bath, right? The exchange would be that you would cool the big body and at the expense of exciting the.
No.
Makes sense?
So the analogy I'm thinking of is blowing in a hot cup of tea, where the few molecules fly off, taking a lot of the energy, and the main body gets cooler. Is that right?
That's right. That's exactly right. Yeah, you're draining the energy of the system by virtue of having a dynamic where small asteroids basically respond as test particles, right? They're kind of along for the ride of the gravitational dynamic, and they can be ejected from the system, carrying energy with them, and the big body circulate.
So I get how that mechanism would force a planet to be more along the orbital disk, because I guess.
Mm-hmm.
Yeah, the main rotation of the entire, like I'm thinking a sphere is rotating, a sphere of garbage is rotating, and a few particles are something going up, something's going down, and whatever's left is sticking towards the middle. I get. How does the main star affect this? Because now I'm thinking, well, sometimes they go out of the solar system, sometimes in. So, well, but usually out, which means the planet has to start moving into the star and collapsing. Wouldn't that happen?
Well, yeah. So the detailed picture is that because you have Jupiter, Saturn, Uranus, and Neptune, okay, what's happening is that Neptune and Uranus and Saturn, they're considerably less massive than Jupiter. Mm-hmm. They are basically playing gravitational soccer with the planetesimals, right? So they're kind of scattering garbage around, and Jupiter is the only thing in the solar system that actually has enough gravity to eject things, okay? Especially in this primordial configuration. As a consequence, indeed, because the stuff that Jupiter ejected started out beyond Neptune and was passed to Jupiter, the conservation of angular momentum necessitates then the orbits of Neptune, Uranus, and Saturn expand. So it's kind of a spreading of the solar system that happens as a consequence of this.
Okay, so they pass to Jupiter and go out, Jupiter ejects.
Mm-hmm. That's right. That's in the early stages. That's true. Once Neptune goes far enough out, Neptune kind of also gets the ability to eject. And that's because it walks out of the gravitational potential well of the sun, right? That factor of 2 is important here, right? So like if you're close to the star, right, you have to not just kick a body, but you have to kick a body and give it enough speed to exceed the escape velocity, and the escape velocity goes down as you go further out. So as the solar system spreads out, Neptune becomes more and more important as its gravity.
Okay, and the last thing is you're showing me, you're showing some evidence saying that you have a consistent pattern of stable orbits that are eccentrical and tilted. Now,
Mhm.
the argument there that if it was unstable orbits, these are the guys being ejected, but these guys, the purple guys, are staying in there. So they've been doing this for a while without being ejected. Something is
Exactly.
keeping them like this. Is that the
That's
argument?
right. That is exactly right. Yeah. So the stuff that's being ejected is sort of, like there isn't much of a footprint in its in their dynamics because it's unstable and it's been messed up in the last 10 to 20 million years. The stable orbits, conversely, are or by some process, right? Whatever it is, that pattern would not stay because each orbit slowly processes around on sort of under million year time scale. If you were to, integrate this forward in time, what you would find is that this pattern would actually symmetrize in like half a billion years. Right? So the time scale is short compared to the life of the solar system. And so if you really believe the patterns and like believe the data, then something is out there keeping these orbits in time.
Got it. Otherwise, they would be symmetric after precession has had a chance to move them around. Got it. Okay.
Exactly. So what is that? That you need a gravitational agent in the outer solar system to get that done. Can you now see this presentation, the slides and the animation?
Yeah, it's good.
Okay. Okay, good. So here, we can introduce in effect any object we want on any orbit we want. But as it turns out, to reproduce the data, to reproduce what we see, you need a body of about 5 Earth masses on an orbit that takes about 10 to 20,000 years to complete one revolution. And it has to be appreciably inclined and appreciably eccentric, as shown here. So in this simulation, we have the orbits of Uranus and Neptune shown as these like small pink circles, and the orbit of a newly introduced planet 9 as the large pink ellipse. And the bodies that you see that are blue and gold are the Kuiper Belt objects. So here we're starting with an axis, perfectly axisymmetric. What you're starting to see is a pattern where only the objects that are anti-aligned with respect to the major axis of the newly introduced planet 9 are surviving. Right, like you guys are all seeing this as well, right? Where the clustering is emerging. So, what's happening mechanistically? Mechanistically, what's happening is as the orbits process through alignment of the eccentricities, as the orbits align, the ellipticities of the Kuiper Belt objects go through a peak. And if you think about what that means that a perihelion closest to Earth, the sun, they get drawn into the orbit of Neptune, and then Neptune ejects them from the solar system. So this is a kind of outer solar system gravitational version of survival of the fittest, or like survival of the stable, where the stable orbits are preferentially being not ejected, and those are the ones that are anti-aligned with respect to the orbit of planet 9. That's how this pattern that we saw gets carved out. Right.
Wait, so
Now,
you're saying
another
anti-aligned? I'm saying wait, they're kind of they're perpendicular to the plane of this thing?
No, they are anti-parallel. So let me find they are anti-parallel. Gosh, usually those are way too. Okay, we might have to watch this whole animation again. But yeah, it's the ones that are, if the orbit of planet 9 swings out to the left,
Yeah.
then all the objects swing out to the other direction. It's actually maybe the best way to think about it is
Okay.
all the purple orbits are pointing downwards, right? if planet 9 is responsible for this, then the orbit of planet 9 would swing out into the opposite direction, kind of also in an eccentric manner.
So I'm getting the impression it's this. This is the picture I'm getting in my mind, right?
So for these guys, it's not a lock. It's more like the infinity sign, or like that marriage sign. You know what I mean? It's kind of like that.
Oh,
Okay, so planet 9 is in the same plane. They're like the reason these guys are 20 degrees inclined.
not this.
Yeah, it's like this.
Interesting. Okay.
Yeah. So the reason they're 20 degrees inclined is planet 9 is 20 degrees inclined with respect to the plane of the solar system, and it's settling them into the same plane as planet 9 itself, while ejecting all the stuff that's collinear with the orbit of planet 9, and keeping all the anti-aligned stuff confined.
So perhaps the intuition I should be thinking of is planet 9 is creating a new orbital plane in that region of the solar system, and anybody who's along that plane lives. Everybody who's not gets just to Neptune and goes away.
Yes. Not right. Not only that, everybody who in that plane dares to align with planet 9, like have the major axes, look the same way, also gets ejected. So as a consequence, you get only the bodies that are pointing the opposite direction.
Okay.
Yeah. Now, I'm glad you mentioned something that we see routinely. So another effect that planet 9 has, which was a bit unexpected, is that it will take some of these objects that started out in the plane of the solar system and twist them out of alignment with the solar system. Right? We can talk about why that is, and this effect related to something called the Kozai effect, but independent of sort of the exact perturbation, understanding of why this happens. This is just a robust result of every simulation that we've ever done. Like these guys that you're seeing here that are popping out of the plane of the solar system, those happen everywhere. So we thought to ourselves, okay, planet 9 itself is a huge challenge to detect because it's a single body. Right? It's a really difficult to conduct an astronomical survey when you're looking for a single object. But if we only found a population of highly inclined, out of the plane of the solar system, long period Kuiper Belt objects, like that could be a line of evidence for the true existence of this thing, because there's no other mechanisms to do it. The solar system starts out as a disk of gas and dust, which is very circular and planar, right? There's no business in the outer solar system, being perpendicular to the plane. And then, as it turned out, such a population of objects indeed exists. And this is the, animation of a small number, a handful of these guys. And as it turns out, indeed, perpendicular to the plane in which the aligned objects here, there is a whole sample of bodies that orbit the plane of the solar system in a perpendicular manner. Look at that in the modern data set. So any is this clear so far?
No, I'm actually confused why perpendicular to the solar system, specifically perpendicular, would be a sign of what is that a sign of?
Yeah, so it's actually not so much the perpendicular, it's not that they go to a perpendicular state and then they sit there. It's that they oscillate in their inclinations, being taken from 0 to almost 180. And it so happens in this dynamic that you have eccentricity peaks at 0, 90, and 180. And at what it means to have an eccentricity peak is that your orbit gets elliptic, means the perihelion, the approach comes in closer to the sun, And then those objects are easier to see. So they're easier to discover astronomically because they appear closer to the sun. And so there's a interplay that's going on between the inherent dynamics that are driven by Planet Nine itself and the observational biases through which we discover KBOs.
So you only see the
Okay,
ones
that's
to the sun.
yeah. You kind of you see preferentially the things that have low perihelion distances, and that's why the kind of nearly perpendicular state is preferred right now in the observational census. I think we are going to do better than this starting this summer. I'll get to why momentarily.
Okay,
But I want to,
but then the intuition is
go ahead.
you're describing a population that is, I mean, there's this preferentiality, but ultimately they're changing their eccentricity, right, during the course of their orbit. And that means what? That there's a body off plane that keeps dragging them periodically? Is that why? Or something else?
Yeah, that's right. So there's the change of the orbital inclination and the eccentricity happens in concert. You can think of it kind of, a cycle where the orbit is both simultaneously getting more inclined and more elliptic at the same time. And the peak of that ellipticity coincides with a 90-degree-ish orbital inclination, which is why you preferentially see those objects.
Okay. Thank you.
Okay. So everyththing I've told you up until now is stuff that we have sort of worked out between 2016 and really 2021. And I've always found it kind of frustrating that there wasn't more evidence for Planet Nine, so to speak. Like, it would be weird that there's a bona fide, 5 Earth mass object in the outer solar system, but we only know because there's a handful of orbits that are like aligned and there's a handful of orbits that are inclined. Like, there should be something else. So we spent the last couple of years trying to figure out what other evidence or what other effects we could chase down. And there turns out there is one. This is from a paper we published last year, and it's actually my favorite line of evidence, even though it's maybe the most boring. And ultimately, it goes down to the question that we just talked about, which is that if Planet Nine is really there, right, then it's driving this oscillation in the orbital ellipticity of the outer solar system. And you can see this oscillation on this middle plot. This perihelion distance, closest to person, distance of closest to person's sun.
Mm-hmm.
It's oscillate up and down. Okay. Now, if Planet Nine is not there, okay, this oscillation is also not there, and that means that no object could exist with a perihelion distance substantially smaller than the orbit of Neptune, because they would be unstable. They would be kicked out of the solar system by, on the timescale of 10 million years. So the solar system should be clear of bodies with perihelion distances substantially smaller than 30 astronomically, 30 times the distance of the sun. And conversely, if Planet Nine is there, then it sustains a flux of objects that are always being injected from the outer reaches of the Kuiper Belt into this sort of giant planet region. Okay. So we decided to do simulations of this, accounting for really every single physical effect that's relevant. Okay, so these simulations, in addition to the giant planet gravitational dynamics, include the effects of the galaxy, right, the galactic tide, the effects of passing stars, all of that done self-consistently in an n-body stream. And what we found is that, indeed, the inclusion of Planet Nine changes the picture dramatically when you're looking at the distribution of perihelion distances inside of the orbit of Neptune. Okay, so again, for reference, Neptune is 30 times the distance between the Earth and the Sun. So that's the top of the y-axis there. Jupiter's at 5. Saturn's at 10, Venus is at 20. So the left-hand side shows you a snapshot of what the is there, and the right-hand side shows you what it should look like if it's. And the color shows the, of course, usual 2D histogram of the distribution. So what you're seeing is that if planet 9 is not there, then objects have a really hard time developing perihelion distance smaller than 30 AU. This is because if their perihelion drops even a little bit interior to Neptune, Neptune just scatters them. Conversely, if planet 9 is there, then you get a pretty flat distribution between kind of 30 and maybe 15. Okay, this is theoretically what should be. Okay, so let's go and look at the data. No, the data looks like this. Okay, this is the top-down view on the left panel of all the well-characterized Neptune crossing long-period Kuiper Belt objects we know of today. Okay, and on the right-hand side, you see the perihelion distribution as a function of the semi-major axis. And I think, again, you can kind of look at this and even before doing sophisticated statistics, convince yourself that this is pretty widely distributed, right? This does not look like the right-hand side panel here. It looks more like this, right? And I should be honest and say that the picture is actually a little bit more subtle. Okay? And the reason it's subtle is, as I mentioned before, remember, objects that come closer to the sun are easier to discover. Right? So observational bias will play a role in kind of widening the distribution, even if it was peak. But the good news is we know how to account for this. What we found is that this population of objects alone rules out a planet 9 free solar system at about 5.5 centi. Right? So conversely, a planet 9 inclusive solar system is indistinguishable from what the data is telling us. So this is like, it's a little embarrassing that it took a decade for us to figure this out, because it's actually kind of a simple line of evidence. You can think of it as this idea. Are there objects that are highly unstable that should not be there in the outer solar system and thus require a continuous flux of being resupplied from the outer reaches of the Kuiper Belt? And the answer is yes. And if yes, you need a mechanism to do that. You need a gravitational dynamic that is going to sustain this flux of objects. And there's nothing that's engineered about these simulations, right? These simulations just include the giant planets that we know, the galaxy that we know, plus the planet 9 that we have already derived from the other population of Kuiper Belt objects, and they turn out to give this population of Neptune crossers that is indistinguishable from what we see in the other solar system. So this is all, fun, but I would say for now, even again looking at the plots, the data sets are limited to sort of tens of objects, right? These are not yet in the hundreds of objects. So this is definitely not in the regime of big data that it's like, because this summer, the LSST, the Vera Rubin telescope, which will drive the survey known as the Large Legacy Survey of Space and Time, that's coming online in like August. It's been under construction for, I don't know, more than 10 years for sure. But it's finally reaching the finish line soon. And the job of LSST is a simple job. It's going to wake up. The telescope is going to wake up every night and kind of look left and right all night, and then the next night it does the same thing. So it's a very, very efficient survey for discovery of these types of long period Kuiper Belt objects. And this is expected, this telescope is expected to have enhanced our senses of long period Kuiper Belt objects by at least an order of magnitude. Maybe so we should be in a couple of years we should know something like 40,000 Kuiper Belt objects rather than the population that we have today. Now it's still not fully clear what the prospects are for just directly detecting Planet 9 with LSST. It might be able to just do it, right? Like this whole conversation might come to a close in a year if this thing just finds it directly, and that's in the realm of possibility. But even if it doesn't, then we will be in a situation where just the statistics will be irrefutable one way or another.
So now, question. Is LSST maybe powerful enough to actually see Planet 9, or is it just the probability of it being close enough to the sun is so low that it's unlikely?
It's not only possible, it's, I don't know, like it's difficult to give a quantitative. Different people have tried to give a different statistical estimate of the probability that LSST will detect Planet 9, and it ranges from somewhere between 100% and like 5%. So I think it's not clear yet, and here's why the jury is out. First of all, LSST is in the southern hemisphere, okay? So it does not reach all of the northern latitudes where Planet 9 could be hiding. And one of the things I maybe skipped over, but I would say now, is that we know the orbit of Planet 9, we know the mass, but we don't know the phase. So we don't know where on the orbit Planet 9 is. And that's because the dynamic through which all of this stuff gets sculpted is kind of a phase average dynamic. It's carved out over long periods of time where it's the kind of average gravity of Planet 9's orbit that together shapes all of these patterns. So we don't know the phase. It could be too north. It also could be too dim. Like we don't know if Planet 9 is reflective or a black bare rock, right? Which would lower its albedo. So that's another. People have written papers, and others have written papers about how it will never be found because it's a completely bare surface that reflects 1% of the sunlight that hits it. So that's it's just a variable that we don't really know how to calculate. So there's a good chance that it'll get detected directly. Even if not, we will sort of know the answer in the same kind of sense as dark matter. Like we know dark matter is there. We don't know what it is, but we know its distribution quite well, right, from kinematics of stars and things. So it would be annoying if Planet 9 ended up in the same camp as dark matter, where we see its consequences, but not its, not the planet itself. But we'll take what we get, and we won't get upset. And finally, the thing that I like about it is that most astrophysics theories have no resolution, no observational resolution that's within a year time scale, right? Most things you're like, oh well, I think this is what's going on, and hopefully a century from now, like we'll know the answer for sure. This is really the different category, right? This is like Planet 9's either there or not there. I think that the evidence is really pointing towards its existence, but I might be wrong, and we will. It's a refutable theoretical model, which is something that I enjoy about.
Yeah, that makes a lot of sense. So let me actually twist this around a bit. So one thing I'm observing about this problem is the only reason why we have any idea this thing exists is because we have a steady population of these. So first of all, we have a pretty stable solar system with a bunch of with 4 heavy planets that just toss things around and clean up space. So you have a clean region that's supposed to exist, a bunch of objects that are supposed to go through it, sampling it periodically like a neutron beam, and they're flying differently from, they should be an empty, they're there, you have evidence. So I'm thinking about all the other kinds of problems that have the same flavor, because it seems like, yeah, like you said, if you swing it the right way, it becomes this obvious analysis. So I guess, is there common threads between the analysis you're doing right now and, well, like traffic detection, where possibly if there's an obstruction, if it's flowing smoothly, that's one mode. If the obstruction is a very notably different mode.
Yeah. So like the problem that comes to mind, and this is just because this is something that I've worked on, is the problem of radioactivation of linear accelerators in like high energy proton beams. It's actually somewhat of a similar problem where the beam it's not gravity, of course. The electrodynamics of the beam tries to tear itself apart and to create this halo of high energy particles, which is bad because then you radioactivate the structure and degrade the operation of the accelerator. But there are ways to confine that halo, and it ends up being identically the same mathematics. So the perturbation theory that goes into that problem and the orbital dynamics problem is not just similar; the variables be the same. Hamiltonians that appear, and so yeah, there are parallels there. But maybe the simplest parallel that you can think of is the parallel of like garbage in the ocean. That garbage in the ocean sinks. It should not be in principle there. There needs to be a continuous stream of garbage that is produced by LA, which sinks into the ocean. Like if you were to not know that LA exists, but to go and swim around in the Pacific Ocean close to the coast, like you would know, you'd be able to infer that there's a large population of people producing a lot of garbage, and it's all going into the ocean. So it's a little bit that, like, there's a similar mechanism of garbage removal, which is just the ocean sinks, the ocean currents carried away. And the fact that it's there now means that it's being replenished on a timescale slower faster than its removal, which is sort of what's going on in the outer solar system.
Yeah, like same thing. How people just detect islands, they look for birds.
Yes.
There's a steady population of birds being spawned from the island, right?
Exactly. Yeah.
Or this also makes me think of, I'll be a little political right now. If you want to infer the effective, I want to say tariff rate, overhead of doing business in a given country, and this is corruption, bribes, any overhead from doing business.
Right.
You effectively start, and you don't have local knowledge, you effectively start throwing packages to/through the country and seeing how much you get charged, and compare it to a disruption-free kind of flow, and that's your effective, like the smooth flow, and there's the obstructed flow, right?
Yes, that's fascinating.
Yeah, I guess also it's called fluid dynamics. Because we have the same property. We have, it should be clean because, like, within Neptune's orbit, it should be clean, right? And
exactly. Yeah. Listen, Greg, I absolutely appreciate this discussion. Really had a great time. Unfortunately, I got to drop off because
You have a
we're about to, yeah, they're about to lock me out of my flight. But
okay, good. Yeah.
yeah.
Have a good flight. Have a good day. Right.
Okay, thanks, Greg. We'll talk again
Bye.
soon at some point. All right.